With Álvaro Pelayo, who will speak on Toric and Semitoric Symplectic geometry, progress and challenges.
Okay, well, thank you very much, Vincent, for the introduction, and thank you very much to all the organizers for the kind invitation. It's a pleasure to speak in this seminar. And so I'm going to speak, as Vincent said, about Toric and Semi-toric symplectic geometry, progress and challenges. So the goal of this talk is to give an overview for non-specialists. I saw in the seminar website that a part of the talk should be for non-specialists, so I'm taking that seriously. So I'm going to give an overview for non-specialists of finite dimensional integrable systems on symplectic manifolds, and then focus on two special types, toric and semi-toric systems. I will also mention quantum applications and open problems. So broadly speaking, there are three parts. First, quick introduction to integrable systems, then I will speak about toric systems, and then semi-toric systems. Okay, so the first part is integrable systems, and I plan to spend about 15 minutes with this. Oops. So a dynamical system is integrable when it has many conserved quantities throughout the motion, for instance, energy, momentum, and so on. And famous example is the shallow water wave, the KdV equation, which is an infinite dimensional system. And it took over 100 years to know that it was integrable. Another example is the spherical pendulum, and today which is finite dimensional. And today I'm going to focus on finite dimension. Oops. So let's see some motivation to study integrable systems and learn about some distinguished historical figures who have been influential in this area and connections with other areas. So there is a sound, which I don't know why it makes this sound. Can you hear a beep every time I move a slide forward? Or maybe it's just me. Okay, so there are many motivations to study integrable systems, including their crucial role in describing phenomena from physics, chemistry, and the other sciences, the connections with general dynamical systems via KEM theory of small perturbations due to Kolmogorov-Arnold-Moser, and the deep connections with topology through the theory of singular Lagrangian fibrations of the Russian school, and also with mathematical analysis. Even more, let's recall what Jürgen Moser told us. The great mathematician Jürgen Moser was a central figure in pushing the development of integrable systems in the 20th century. A world-leading figure in analysis, Moser was professor at MIT, NYU, and ETH Zurich. And in the proceedings of his plenary talk at the ICM in Berlin, about 25 years ago, he tells us it is impossible to even touch on the many ramifications which have evolved from the study of integrable systems. And he continued, Moser, who had a deep knowledge of many areas of pure and applied mathematics, continues to say, most striking to me is the development of integrable systems some 30 years ago, which did not grow out of any given problem, but out of a phenomenon which was discovered by numerical experiments in fluid dynamics. And Moser continues to say, intelligent studies and deep insight open up to a novel field impinging on differential geometry, algebraic geometry, and mathematical physics, including applications in communication of fiber optics. So this gives you an idea of the breadth of knowledge of the subject of integrable systems with words from one of the masters of analysis, and in particular, who made very important contributions to integrable systems, who was Moser, Jürgen Moser. Okay, so integrable systems are studied from many viewpoints. A lot of authors have made pioneering contributions, including Arnold, Doisemat, Eliasson, Fomenko, Gieleman, Hitchin, Kolmogorov, Kovalevskaya, Langlands, Moser, Netter, Vyshitikin, Uhlenbeck, Weinstein, among many, many other authors. So in particular, recently the Norwegian Academy of Sciences and Letters awarded the 2019 Abel Prize to Karen Uhlenbeck for her pioneering achievements in geometric partial differential equations, gauge theory, and integrable systems, and for the fundamental impact of her work on analysis, geometry, and mathematical physics. Today, I'm going to focus on finite dimensional integrable Hamiltonian systems from the point of view of symplectic geometry and topology. Okay, So how are these systems defined in this concrete context of symplectic geometry? We see it next. So let M to N be a 2n dimensional symplectic manifold. A smooth function f1 through fn on M to N is an integrable system if two conditions hold. The first one is commutativity, which means that each function fi is constant along the flow of xfj for all ij, where xfi is given by the equation xfi equals minus dfi. So this is the Hamiltonian vector field generated by the function. Okay, you have the symplectic form, which is a 2 form. On the right hand side, you have this 1 form, and there is a unique solution, which is this vector field. Okay, and the second condition is independence, which means that at almost every point, the vector fields xf1 through fxn are linearly independent. And an extra hypothesis for today is that the fibers of the system are going to be assumed to be compact, and also throughout the talk, here and elsewhere in the talk, all manifolds are assumed to be connected. Okay, so historically, the term integrable comes from considering a symplectic manifold of dimension 2n and a function called the energy function or Hamiltonian, h on the manifold, and M, the manifold endowed with this function, is called the Hamiltonian system. And what are the integrals of h? They are functions which commute with h, and which are pairwise independent, that is, functions satisfying the conditions I just gave in the previous definition. So is there a maximal number of integrals? And the answer is yes. With the conditions, there are at most n-1 integrals, f2 through fn. And in this case, the Hamiltonian system, M endowed with h, is called integrable. However, the modern viewpoint is to consider all integrals simultaneously. So to consider the map h, f2 through fn on the manifold to Rn as the integrable system. And you can have generalizations of this. You can have more than n-1 integrals by relaxing the conditions, and you get things like superintegrable systems, etc., which are also very, very interesting. Okay, so what does a typical integrable system viewed as a function look like? So here you can keep this picture in mind. We'll come back to it later. You can see the fibers are pinch tori, points, circles, or two-dimensional tori. Okay. So next I'm going to present 4 examples of integrable systems which are very well known and with explicit formulas. Okay, so the first one is the complex projective space, which is an example of integrable system, which is very important in algebraic geometry. It comes endowed with the Fubini Studi symplectic form. I'm going to skip the formula. And this integrable system is given by these n components, f1 through fn, and each of them is given by this formula. And is known, as you know, it is induced by a rotational action of a torus on the complex projective space. Another example is the James-Cummins model, which is an integrable system, f1, f2, with defined on the product S2 cross R2. And given by these 2 formulas, where x, y, z are coordinates on the sphere, u, v are coordinates on the plane, and S2 cross R2 is endowed with the product form. So an area form on the sphere and this form, the u wedge dv on the plane. And this is a crucial model which explains fundamental physical phenomena, and it's been studied in many physics papers. It's also been studied in some of my papers and other papers in mathematics and mathematical physics, and it originates in James and Cummins in the 1960s. Okay, so probably all of you or many of you already recognize that this F1 corresponds to the momentum map of a Hamiltonian S1 action, which rotates on the plane like it shows in the figure about the origin, and on the sphere about the vertical axis. So one of the most famous integrable systems is the pendulum, which goes back to the 17th century. How does one describe it mathematically? The spherical pendulum is another example, which is fundamental in physics and goes back to Huygens. And mathematically, it is given on the cotangent bundle of S2 by these 2 integrals, F1 and F2, where F1 is the sum of kinetic energy plus potential, And this first integral f2 is given by psi phi, where theta phi are spherical angles with phi being rotation angle about the vertical axis, and theta measures the angle from the North Pole. And psi phi, psi theta, psi phi are the cotangent conjugate variables. So this is another crucial example of integrable system. And you can see these last two examples are on four manifolds. Lastly, it is impossible not to mention a system as important as the coupled angular momenta of Sadowski and Zielinski. It is an integrable system essential in physics. So to give formulas, I'm going to consider two positive values, R2 and R1, and coordinates x1, y1, z1 on the first sphere, and analogous for the second sphere. And the integrable system is given by these two formulas, where the second one, we make it depend on a value of t, a fixed parameter t, and are given by these two expressions. And on S2 cross S2, we have the symplectic form, which is the product form, which comes given by the sum of two area forms on the spheres. So this is a compact examples. The four manifold is compact, S2 cross S2, and in the previous two examples, some of the previous examples we had non-compact, like in the case of the James-Cummins, for example, James-Cummins model. Okay, so let's see a great challenge in the field. In mathematics, equivalent objects are called isomorphic. So when are two integrable systems F1 and F2 isomorphic? So being isomorphic means that there is a diffeomorphism of the underlying manifold, which exchanges the systems and the symplectic forms. And an invariant is an object or property that isomorphic systems share. So a great challenge for the 21st century, in my opinion, is to construct invariants, say I1 through IK, that classify integrable systems in terms of them. So we want to understand something difficult, integrable systems, in terms of something easy, invariants, in principle easy. So what do we know about the previous challenge? First, it has quantum applications to inverse problems, which I will mention. It is known how to solve the challenge, so to construct local invariants in a neighborhood of a point, and almost nothing is known about semi-local invariants in a neighborhood of an orbit, nor global. I'm talking about symplectic invariants. After 1988, the work of Atiyah and others, the most successful techniques have been cut and paste techniques developed with collaborators in various papers, in particular in an Invenciones and Acta paper in 2011, 2009 and 2011, and in a paper in the Annales de l'École Normale. And the upcoming theorems are going to be about this. So to address this challenge, it is necessary to understand integrable systems in a neighborhood of a regular singular point and in a neighborhood of a regular singular orbit or fiber. But we know little about this, with the exception of a result by Arnold and Minot that many of you will know, that says that if the vector fields xf1 through fxn at M are linearly independent, then we know we call the point regular. And the famous action angle theorem says that a fiber with only regular points is an n-torus, which sits inside of the cotangent bundle of the torus. And in a neighborhood, the integrable system fx1 xn psi1 psi n is just projection psi1 psi n. This is, of course, assuming the preimages of compact sets are compact. If not, there is another version which is very similar. And there is a global version of this result by Hans Doisemann in a very important paper in 1980. But the most important information about an integrable system can be found in its singularities. These are the points M, where the vector fields xf1 at M, xfm at M are linearly dependent. For examples, in this figure, you can see these pinch points here, M0, M1, M2, etc. These are singularities of the system. So remember our earlier figure of a typical system on a four manifold. This is a singular Lagrangian vibration, and the regular fibers are two tori. You can see these two tori, and the fibers with singularities are either points, circles, or pinch tori, okay, where you have these pinch points which are singularities. Now, we do not understand most of the symplectic invariants of these systems, with two exceptions, the toric and semi-toric cases, which I mentioned in a moment. To conclude this part, I want to make a remark that the singularities, to make a remark and state an important theorem, that the singularities of integrable system corresponds to critical points of this function, f, That is the points where the rank of the differential at M is strictly less than N. So expanding in power series, you can ask the question, what are the local models of F? And the answer is that very few and without higher order terms. So let's see, this is a very important result. This is a deep analytic theorem by Eliasson, which was proven in certain cases, like the analytic case and some other cases earlier. So this is the smooth case. It is known since the early 80s that an integrable system without hyperbolic singularities is given in a neighborhood of each singularity in symplectic coordinates x1, xn, psi1, psi-n by the following models, q1 through qn, up to composition on the left by a diffeomorphism, and where omega has the standard form. So the models can be elliptic, real, and focus-focus, okay? And there is also a version of this result very similar with hyperbolic singularities, which is the last only possible model. But today I'm not going to be discussing hyperbolic singularities, so I prefer to state it in this way. So you can see exactly what the models look like. And also for this talk, I'm going to assume that the singularities are non-degenerate. This is in a precise Morse-Bot sense for multivalued functions, which I will not discuss, but it can be made precise what it means. Here you can see the images of singularities in dimension 4. So you can see, for instance, regular value, the focus values, which are rank 0 singularities, the elliptic singularities, which are rank 0 singularities, and so on. Okay, so this concludes this first part, the integrable systems. And I recommend for this part, for an introduction, my papers in the bulletin of the American Mathematical Society in 2011 and 2017. The paper in 2011 is joined with Sam von Gogh. Okay, so let's solve the challenge I mentioned about classifying systems in terms of invariance in two important cases, the toric and semi-toric. And I'm also going to see some related results and challenges and applications to quantum geometry. So I start with the toric systems, which is the longer part of my talk. So here you can see two examples of toric systems. The first one corresponds to CP2, and the second one corresponds to CP1 cross CP1. And as you can see, there are no pinch tori in this case. In fact, an integrable system F1 F through Fn is called toric if the vector fields xf1 through fxn generate periodic flows of the same period. And the fundamental example is the one we just saw, CPn. And there is a famous theorem in the early 1980s that says, by Atiyah and Guillemin Sternberg, that says that if the manifold is compact and F is toric, the classical spectrum, like is this called in physics, so that the image of the system, F of the system, is a convex polytope in Rn. This is what Atiyah and Guillemin Sternberg proved. And in fact, this polytope can be checked that is simple, rational, and smooth. These polytopes are named, in fact, in honor of Thomas del Sant. So the polytopes we just saw carry his name. A del Sant polytope in Rn is a simple, rational n polytope such that the primitive edge direction vectors at each vertex are a basis of Zn. This last condition is what is known as smoothness of the polytope. So the set of these polytopes is going to be very important for me. I'm going to call it Dn, the set of all del Sant polytopes in Rn for a fixed n. And here you have an example of perhaps the simplest example of toric system, which is the just given by one integral on the sphere, which is the height function. And as you can see, the image of the moment map is this interval -1, 1, which is the convex hull of the images of the two fixed points of the system, which are the north and south pole. In fact, in the decade of the 1980s, building on ideas of Atiyah, Guillemin, Horn, Kosten, Schur, Sternberg, and others, Thomas del Sant proved that the correspondence which sends an isomorphism class of a toric system to its image, f of m, is a bijection between the isomorphism classes of toric systems and the set of simple, rational, smooth polytopes. That is the set of del Sant polytopes. So this is a very impressive, extremely interesting result. And around the influence of this theorem and related ideas, strong research groups developed at different universities, including Harvard, MIT, and UC Berkeley. And I was fortunate to spend some years myself at MIT and UC Berkeley. Okay, so thanks to these impressive theorems, problems about toric systems can be posed as problems about polytopes. So these theorems give a bridge between two worlds. So the disadvantage, why translating problems from manifolds to polytopes? So the disadvantages is that the combinatorial problem may not be any easier. Translating the problem back and forth is technical, but there are some advantages, which is that since the 1990s, there's been major developments about polytopes, and some problems in geometry, once translated, appear to be more doable, seem more concrete. So I'm going to take advantage of this viewpoint in the talk today. So, but I should mention that the conclusions of these theorems by Atiyah, Guillemin, Stenberg, Delsan are so strong because the singularities of toric systems are the simplest ones. That is, they cannot have focus nor hyperbolic models. So locally in a neighborhood of a point, the system looks like, has this form, has a few components of elliptic type and a few regular components. So in particular, the fibers are diffeomorphic to tori of varying dimensions from points to full dimensional tori. So here on the left, you have the same picture again that I showed earlier of a toric system on CP2 and on CP1 cross CP1. And here you have fibers, points, circles, or two tori. The previous theorems have extensions to a variety of cases where the symplectic manifold is replaced by a more general or complicated space. And for example, there is an extension to log symplectic manifolds, which I did with Lee, Gualtieri, and Ratio. There is an extension to non-compact manifolds by Carchon and Lerman, and there is an extension to orbifolds in a well-known paper of Lerman and Tolman. So toric integrable systems provide useful examples, and many problems about them are still open, including some famous conjectures. So what are some of these problems? I'm going to show you a sample next of the ones I've been interested in the past 3 years or so. So a natural question is, what is the structure of the set M to N? I'm going to use this notation, M to N, of isomorphism classes of compact connected toric systems. So to give this set a structure, what I'm going to do is I'm going to take advantage of the Delsan correspondence and define a structure on the set of polytopes, okay? In other words, this can be answered using polytope theory. Let's see how next. So let's see N, the set of compact convex sets in Rn, and I'm going to define the symmetric distance and the Hausdorff distance by these well-known formulas on this set. And I'm going to call CPN, and this is important, to the set of proper ones. That is the set of compact convex sets with non-empty interior or positive volume, which is equivalent. On CPN, on this set of proper compact convex sets, these two distances are not equivalent, but they induce the same topology. So we endow the set of Delsan polytopes with this topology. And we endow the set of 2n-dimensional toric manifolds, isomorphism classes, with the metrics and topology induced by this identification given by the Delsan correspondence. And it can be shown that this set, this modular space of toric systems, is path connected and dense in the set of proper convex sets. And this is a statement that for 4 manifolds is due to myself, Pires, Batio, and Sabatini. And in that paper in 2014, 10 years ago, we asked the question for 2n, for arbitrary dimension. And we were able to do it, Santos and myself, in a paper last year, the arbitrary case, arbitrary dimensional case. And the same papers solves several problems by Fujita, Kita-Beppu, and Mitsuishi. Most of the paper is metric geometry concerning delta V and delta H, and there are a number of other results, but I'm going to skip them in this talk. So another natural question is, what happens with blowups of toric integrable systems? And this can also be answered using polytopes. So let's see let's see how this can be done next. So a lattice polytope is a polytope with integer vertices, and a reflexive polytope is a lattice polytope such that every facet supporting hyperplane is of this form, uf.x equals 1, where uf is the primitive vector normal to the facet. These polytopes are very well known. And equivalently, a reflexive polytope is a lattice polytope whose dual has also integer vertices. And every reflexive polytope has the origin as the unique interior lattice point. Hence, for reflexive polytopes, a fine GLNZ equivalence is the same as GLNZ equivalence. And throughout this talk, when I talk of a polytope, I usually talk about this GLNZ equivalence class of the polytope. So here is a very interesting class of polytopes, which to many symplectic geometers, the name monotone already suggests the idea of monotone symplectic manifold, which I'm going to discuss next. But first, what is a monotone polytope? A monotone polytope is a Del-Sanan reflexive polytope, and you can see how many of these you have per each dimension. And a monotone blow-up of a monotone polytope is a blow-up which corresponds to chopping of a vertex that results in a monotone polytope. So here you have the only 5 two-dimensional monotone polygons. So some terminology then, and an n-simplex is the convex hull of its n+1 vertices, and the smooth unimodular n-simplex is given by delta n, the set of points in Rn, such that all the coordinates are non-negative or their sum is at most 1. And there is only one monotone n-simplex, of course, modulo GLNZ, which is -1, -1, -1 plus n+1 delta n, which is isomorphic combinatorially to n+1 delta n. So here is a question about these polytopes, which Dusa McDuff asked in 2011. Is there a monotone polytope of dimension n greater than 2 for which one can make at least 2 monotone and disjoint blowups of points, and or more generally of any 2 faces of codimension strictly greater than 2? Okay, so this is a question that I was interested in from after I read this paper. So before we answer the question, let me show you a little more about monotone 3 polytopes. So there are 5 maximal monotone 3 polytopes, which corresponds to this figure. And here, when I say maximal, I mean respect to the inclusion. And in dimension 3, they coincide with those that cannot be obtained as a blow-up of another monotone polytope, but this is not the case in arbitrary dimension. Okay, so let's answer McDuff's question. The first result is a polyhedral version of a result by Bonavero. So this is a result that is due to Bonavero. The only monotone polytopes that admit one monotone blow-up at a point are the monotone n-simplex and the blow-up of a codimension 2 phase of it. And this implies, and the full answer to the question is given by this second theorem. No monotone polytope of dimension n greater than 2, strictly greater than 2, admits 2 monotone disjoint blowups at points. And the monotone n-simplex admits disjoint blowups at faces f1 and f2, if and only if f1 and f2 are disjoint and their codimensions add up to either n+2 or n+1. So if n is at least 4, the monotone n-simplex admit 2 disjoint blowups at faces of codimension strictly greater than 2. So this gives a full answer, a complete answer to the question by McDuff. Okay, so I'm not gonna spend much time on this, but in case someone wants to look at it later, this diagram has a representation of the 18 monotone 3 polytopes according to the number of 2 faces and the relations through blowups. You can consult this later if you want to. So the previous results concern polytopes, but I've been talking about here the possibility of translating results from manifolds to polytopes. So what do these previous results about polytopes tell us about toric systems? So first I want to make a remark that in symplectic and algebraic geometry, toric systems are usually called symplectic toric manifolds, to emphasize that the system induces a Hamiltonian n-torus action on the manifold by concatenation of the flows, of the Hamiltonian flows of F1 through Fn. So depending on the context, I use both names. In dynamical systems, more frequently people use toric systems. In equivariant symplectic geometry and group actions is more often used the name symplectic toric manifold. Okay, so now I come back to I state this definition, which is familiar to probably everyone, which is a compact symplectic manifold of dimension 2n is monotone if there is a constant lambda positive, such that the class of omega is lambda times the C1 of the manifold. By rescaling, we may assume lambda equals 1, and delta, the polytope delta, is monotone if and only if it is the momentum polytope of a monotone symplectic toric manifold. So there you have the relation between the manifold level and the polytope level through the system. That is, via the Delsan correspondence, monotone symplectic toric 2n manifolds are the same as monotone n polytopes. And we understand this relation in a completely explicit way through the Delsan correspondence, which sends a system to the image of the system, which is what is often called in physics the classical spectrum. Okay, so with this in mind, I'm just translating the previous results to the symplectic world, the results about polytopes. So there is no new ingredients here, it's just a translation, okay? The translation says that the only monotone symplectic toric manifolds that meet a monotone toric blowup at a point are CPN and a blowup in CPN at a C-star n orbit of complex codimension 2, and CPN admits two disjoint monotone toric blowups if and only if the exceptional divisors of the blowups have complex dimensions adding to n-2 or n-1. So this is exactly a translation of the previous results from the world of polytopes to the world of manifolds. Now, there is a famous conjecture from the 1980s by Gunther Ewald. So I want to discuss this conjecture now concerning monotone geometry, and a generalization of this conjecture by Benjamin Neal from 2009. So in fact, these conjectures have symplectic implications. So let's see what we can say about them. So this is the conjecture by Ewald from the 1980s. It says that if P is a monotone n polytope in Rn, then the set Zn intersection P intersection minus P. So if you think about it for a second, you see that this is just the set of integer points which are symmetric. So if a point is in the set, the negative of the point is in the set, okay? The conjecture is that this set contains a unimodular basis of Zn. In other words, the standard basis of Zn up to GLNC transformation. And Neal asked if this generalization might hold. The generalization is, we call it the general Ewald's conjecture, that says that if P is a lattice Delsan polytope, n polytope, with origin in the interior, then the set of symmetric points contains a unimodular basis of Zn. So this is Ewald's conjecture is a fascinating conjecture with a very simple statement, and not much is known about it. Or there are, I mean, we have contributed some results in the past year, but it's been open for a very long time, and the general case is still open. So up to n equals 7, Ewald's conjecture was proven by Obro using computational software. You see, you have this collection of monotone polytopes, and you can test the conjecture on every one of them. The 2023 preprint by myself with Crespo and Santos contains a theoretical proof of Ewald's conjecture in arbitrary dimension for a broad class of polytopes. And also the paper contains a proof of the generalized conjecture for n equals 2, and a proof of the generalized conjecture for n equals 3 up to a minor hypothesis. And the case n equals 4 or higher is completely open. So I'm not going to state the results here, but you can check them in this paper. So this is all very interesting, but many of you are probably wondering, does Ewell's conjecture have applications in symplectic geometry? The answer is yes. In fact, I was interested in this conjecture precisely because of the symplectic geometry angle. So I learned of this connection in the work of Dusa Magdaf. So what do symplectic geometers care about Ewell's conjecture? So this is a very long story, but I'm going to just give a glimpse of why we care. So Ewell's conjecture is connected with the problem of when the fibers of a monotone symplectic toric manifolds F inverse of C are displaceable by a Hamiltonian isotopy. And there is important work about this by Biran and Tov-Polterovich, Cho, and Magdaf. And being displaceable at the level of manifolds can be studied at the level of polytopes via ideas related to this conjecture. So this is why I was interested in this conjecture. So in view of the work of Brendel, recent work of Brendel, the work that I just described with Crespo and Santos on the conjecture implies that if the classical spectrum f of m belongs to a certain class of polytopes, to define this class would take me some time, so I'm not going to do it, then the Chekhov torus can be embedded into the monotone symplectic toric manifold M2N to yield an exotic Lagrangian, which is not real. So this statement is not ours. This statement corresponds to Brendel's result. And our contribution here is to explicitly give the class U. So I would like to thank Brendel for letting us know about this very interesting connection, which I was in particular very pleased to hear about. Okay, so conclusions. Some problems concerning symplectic toric manifolds can be translated into problems about polytopes. Perhaps a similar translation can be done for more general integrable systems. This has given rise to new problems in combinatorics. And from the point of view of symplectic geometry, the answers to the combinatorial problems may have crucial consequences, as I think I've shown in some examples. Okay, so I mentioned in the title of my talk that I was going to mention some challenges. So in my opinion, Ewell's conjecture is definitely a challenge. As you saw, we have proven some cases. We have proven the conjecture for a broad case of polytopes in arbitrary dimension, but there are still many cases left. So the conjecture has symplectic implications, and some symplectic problems can be solved as problems about polytopes. Now, what are some key problems about polytopes which can be solved as symplectic problems? In other words, I have shown, or I have taken some problems in symplectic geometry to polytopes and then solve the problem with polytopes and then make a statement about symplectic manifolds. And I wonder if also there are interesting problems where you can take original problems from polytopes or combinatorics to the symplectic category, solve them with symplectic tools, and then come back to the combinatorics polytope category. There are probably examples of this already, interesting example. It would be nice to know more examples. Okay, so I conclude the second part, speaking very briefly about quantum integrable systems. And of course, I'm going to focus on the toric case, which is this second part. The hope is that from quantum spectral information, we can extract a lot of classical information. So first, let's see what we mean by a quantum integrable system. I'm going to give a general definition. And of course, if you want to make some things concrete, it takes a lot of work, but let's give a general definition. So to start with, let Hk, where k is a natural number, be Hilbert spaces quantizing a 2n-dimensional manifold M2n. There is a famous method to do this in certain cases, the Costan and Soriao geometric quantization, and I learned about it from Berg-Costan, papers of Berg-Costan, and also from talking to to him when I was at MIT. And also I learned about this as a student from a memoir that wrote one of my colleagues in the Royal Academy of Sciences in Spain, Pedro Luis Garcia. Okay, so the definition of quantum integrable system is as follows. It's given by n self-adjoint commuting semi-classical operators, xi1 through xi(n). Each of them depends on contains a sequence depending on a value of k, acting on these Hilbert spaces whose principal symbols form an integrable system on the manifold. And then its semi-classical spectrum, or simply the spectrum, is the support of the joint spectral measure, which if these spaces are finite dimensional, is for every k natural number is this set of points in Rn, one for each value of k. So it's semi-classical because you have one for each value of k, or if you like, one for each value of h bar. The Planck constant, but I see that I'm going to mention it in the next talk, in the next slide. So to make these notions, quantization and principal symbol precise is technical, depends on the context, whether you have compactness or not, and is beyond of the scope of what I want to say today. But for an introduction to this, you can see my entry speech at the Royal Academy. There is a video where I explain slightly more than today about these quantum systems. And also there is a talk which I gave last year in Madrid, where I also explain a little more. But for more extended explanations, you can check my papers in the bulletin of the Belgian Math Society, the analog of the Col Normal with Logan Charles and Sam Van Gogh, and also my paper with Leonid Polterovich and Sam Van Gogh in 2014 in the proceedings of the London Math Society. Okay, so very roughly, when I say very roughly, it's really very roughly, if the manifold is compact and connected, these Hilbert spaces HH are given by the space of holomorphic sections of tensor powers of some line bounds, a certain line bundle LK over the manifold, and our semi-classical very symplectic operators are sequences T equals TH, defined on these Hilbert spaces, where F is viewed as the multiplication operator that has an expansion, asymptotic expansion, F0 plus K inverse F1 plus K negative 2F2, etc. for the C infinity topology. And here pi H is the surjective orthogonal projector, and F0 is the principal symbol of T. Okay, so all of this can be made precise, depends on the context, and it can be very tedious to make this concrete and rigorous. And you can check the previous references and the reference that you can find in those. Okay, so this allows me to state the inverse problem for quantum integrable systems, which goes back to Weil and Wagner at the end of the 19th century, and then it was made popular by Moser and by Kac in the 1970s and 60s. The question is, given the semi-classical or quantum spectrum of a quantum system of semi-classical commuting operators, what information about the classical system of the principal symbols F1 through Fd can be obtained from this spectrum? Okay, so I'm interested on this problem for quantum integrable systems. You can also pose it more generally and for semi-classical commuting operators, and there are some results, for instance, in the paper by Polterovich, Van Gogh, and myself for this more general case. So there is a general principle in quantum mechanics which says something very interesting about this Weil-Wagner-Moser problem, which is the correspondence principle that says the behavior of quantum observables converges in the high frequency limit of semi-classical after rescaling to the behavior of the classical ones. And as an example, it is generally known that the quantum spectrum converges to the classical spectrum. That is the image of the principal symbols. And here you have the eigenvalues, and you can see as the value of the K increases or the H bar decreases, the eigenvalues fill up completely the inside of the classical spectrum. This is an actual system. And there are pioneering results about this by Colin de Verdier at the end of the 1970s. which were extended by many authors, and in particular by Paul Terovich, Mungok, and myself, to the Beresin top list case. So in principle, we can recover the image of the classical system from the quantum spectrum, and we saw for toric system that this image is just a polytope, which is the only invariant. So if we verify convergence, then we are done. So how about for general systems? The spectrum is unlikely to contain all symplectic information of the principal symbols, but since we understand very well toric and semi-toric systems, so we should have some hope that we can give good answers to this. And so let's see what happens in these cases next. So using symplectic geometry, next I'm going to solve this inverse problem for toric systems. So what is a toric system? A quantum integrable system psi1, psi-n is toric if the principal symbols form a toric system. So it's the only possible definition, or the obvious definition of quantum toric system. So I'm going to state the theorem now with Logan Charles and Sam Bungok. Let psi1, psi-n be a quantum toric system on a compact manifold. Then the spectrum of the system converges to the classical spectrum. And you can recognize this figure is a Hirsebruch trapezoid. Okay, so it corresponds to a quantum toric system on a 4 manifold. So the spectrum determines the classical toric system given by the manifold and the principal symbols. Okay, so it's very easy. The spectrum converges to the polytope, and we know by Del-San's theorem that the polytope determines the toric system. So we are done. Hence, the challenge is solved for toric systems, and the same paper shows that toric systems on compact manifolds can be also quantized. So here you have well, we conclude this part, and here you have some references to papers that I mentioned today. And also I have included a paper that I really like with Hans Deusemat which talks about the comparison between the toric variety and the symplectic toric manifold viewpoint when studying toric systems. Okay, and here you have, for instance, these last 3 papers concern Ewald's conjecture, and the other questions about moduli spaces and blowups. Okay, so toric systems are very interesting. However, they are rare in the physical world. Why? The periodicity of all flows is too restrictive. So what is some flow is not periodic. Then these systems are called semi-toric, and there are many. For instance, the James-Cummins model and the coupled angular momenta. So let's see it. So I start this last part, which is 15 minutes, hopefully a little less, so I can end on time. So here is a typical semi-toric system viewed as a map. In this case, you can see you have the same fibers as before for toric systems, but now you have these very interesting fibers, which are tori, which are pinched multiple times. So you could have a tori pinched 5 times, a torus pinched 2 times, a torus pinched 3 times. So it gives an incredible breadth of richness to the situation. So an integrable system on a symplectic 4 manifold is semi-toric if the vector field xf1 has a periodic flow, but we do not ask anything of the second vector field. And okay, and you're probably thinking, well, now he's focusing on dimension 4, and before there was a theory of toric systems in any dimension. And you are right. We would like to have a theory in any dimension, but that is a great challenge. And for the moment, our results are in dimension 4. So we only have 2 integrals. But I should say that this situation gives makes the system much richer than in the toric case, even in dimension 4. So M4 may not be compact, but for the moment, in order to prove things, we also require that F has no local hyperbolic models, the preimages of compact sets are compact, and each fiber of F1 has at most 1 focus point. Okay, this is called simplicity. The term semi-toric is discussed in a paper.
Yeah, sorry,
yes.
sorry. There's a question in the chat.
Sure. What should I do?
Can you see it, or maybe I can?
So
what
I have to click
complicates?
the tab.
Yeah, what
Maybe you can
complicates?
tell me?
Yeah, what
Maybe
complicates?
Yeah, go ahead.
What complicates the abstractions to higher than 4 dimensions?
So, so all the invariants, I'm going to explain next what are the invariants in dimension 4. In higher dimension, so there are great difficulties. For instance, the singular fibers and the singularities have a great amount of freedom. And at the moment, we only understand well singular fibers in dimension 4. If we talk about classification of a symplectic classification of fibers in arbitrary dimension, then this is very complicated and is not known. So this is a great difficulty. So to summarize, the singularities are much more complicated, the fibers are much more complicated. And then there is another crucial difficulty, which is that one of the invariants I'm going to explain next of semi-toric systems is a polygon. This polygon is a generalization of the polytope of the theory of Atiyah and Gilleman-Sternberg. But in higher dimensions, this polytope is very difficult to have a polytope. There is some work that has been done in dimension 6, okay? But in arbitrary dimension seems extremely complicated. So why we don't have a polytope in higher dimensions? Well, here the crucial observation is that the image of a semi-toric system in higher dimension is not a polytope, is some arbitrary region with some properties, okay? And to turn this into a polytope is very complicated. And so something has been done in dimension 6, which is interesting, by Christophe Boischaud, but in arbitrary dimension, I would say this is out of reach. So these are basically the two reasons. And the polytope basically encodes the singular affine structure of the system. And we don't know how to deal with that at the polytope level in higher dimensions. And also the second point would be singularities, and singularities have a lot of freedom. Singular fibers have a lot of freedom, and it's just not easy to deal with. And if you want to add even more complexity, you could ask the question, what happens if you have hyperbolic singularities? And some work about this has been done by several authors, but it's also quite complicated. So yeah, second question. There was another question, or?
No, I think that's it. Thank you.
That's it, okay.
Sounds
good.
Continue.
So I think the answer to the question is also going to be, I'm going to be mentioning why it is hard in a few minutes, emphasizing what I just said. So the term semi-toric is discussed in a recent paper in honor of my college geometry teacher, Professor Sanjurjo. And in contrast with the toric case, many physical models are semi-toric, like the ones we saw earlier. So let's recall them. These are my favorite systems, the coupled angular momenta and the coupled spin oscillator, which is also called the James-Cummins model. So these two systems are semi-toric, but of course they are not toric. They have pinch fibers, which are torus pinch ones. So in essence, a semi-toric system is like a toric system, but in addition, it has these very complicated singularities of focus-focus type, okay? Remember, I'm ruling out hyperbolic ones. And in principle, going back to the question you asked me, in principle, in the future, we would like to have hyperbolic singularities, etc., included in the classifications. And some work has been done about this by several authors in the past few years. So how are these more complicated singularities reflected in the list of invariants? So before there was in the toric case, there was a polygon, and now there is a polygon and some labels. So let's explain this next. So a semi-toric system, if given by these two integrals on a compact or not four manifold, is symplectically determined by a polygon constructed from its classical spectrum and points P1, Pn in the polygon labeled with an invariant K and another invariant, which is a Taylor series. So pictorially, a toric system is encoded by a polytope. in arbitrary dimension. Pictorially, a semi-toric system in dimension 4 is encoded by a polygon, okay, and some points inside and some labels. And you can guess that these points inside are going to be focus values. They are going to come from the focus singularities of the system, okay? And each of them has comes endowed with an integer and a Taylor series. And these P1 through Pn are focus values. K encodes the topology between fibers, and the Taylor series encodes the behavior of the Hamiltonian vector fields of F1 and F2 as in a near this fiber which contains the focus point, okay? And this invariant, this Taylor series, is an invariant which is defined in the case of 4 manifolds, okay? And so is the polygon. So if we want to move to higher dimensions, we have to see what these invariants are. And in dimension 4, these focus singularities, these focus models, which I explained earlier, they come in pairs, but now maybe in higher dimensions, you mix them with other models, and this can get very complicated. Okay. So the proof of this theorem, it uses ideas and techniques and is related to the work of many people. You can check this later if you want to. But the theorem I just described is a uniqueness theorem. So next I want to follow up with an existence theorem. And you can see that the Delsan correspondence gives you existence and uniqueness. Okay, so the theorem I just described is a uniqueness theorem. Two systems are isomorphic if and only if they have the same polytope with these points and labels. So I want to now do an existence result. So the existence result, this is a paper with Sam Van Gogh, of which we are very proud, in Acta Mathematica in 2011, that says from the purely combinatorial information of a rational polygon delta with certain properties and points P1 through Pn in it, each of these points labeled with an integer k and a Taylor series, one can construct a symplectic 4 manifold and a semi-toric system on it, whose invariants are this polygon and these points and these labels. So you really you can do a construction from abstract, purely combinatorial information of a symplectic 4 manifold and a semi-toric system on it, whose invariants are precisely given by this abstract information, given by the polygon, the points, and the labels. So this result is another bridge between, on one end, symplectic geometry of integrable systems, and on the other end, a mixture of combinatorics, the polygon delta analysis, the Taylor series, and topology, this invariant K. Okay, so the proof is based on new cut and paste techniques. One, basically, roughly speaking, one cuts delta, the polygon, into pieces over which you have action angle variables, and then you paste together these pieces and obtain a continuous system F to which you glue or attach the fibers of the focus models given by the Taylor series. Now, in this way, you obtain a system which is extremely singular on the overlaps, and to make it C infinity smooth is what takes most of the paper and is the hard part. So an indication of the good health for a subject is that there are many people working on it from different angles. So I conclude this part by mentioning a few active avenues of research in these toric semi-toric worlds: computation of invariance, extensions of the theory, and moduli spaces. So since I'm already pretty much done with time, I'm going to very quickly say that you can do concrete computations for the couple angular momenta, and you get a polygon and a Taylor series. So we can, it's not easy, but you can do computations of invariance, and many authors have done this. For instance, you have some papers which concern computations of invariance. Now, very briefly, concerning extensions, there is my PhD students, Joey Palmer and Shudi Tang, and I extended the classification of semi-toric systems to the case where you have several focus singularities per fiber. This is what is called the non-simple case. And we proved that in this case, the symplectic invariant is a convex polygon with some points inside and some labels. And the difference with the previous case is that you can have more Taylor series than one, because there is one Taylor series per pinch point. So the invariance case is also more complicated, and there are several series per point. When there is one pinch point, in the fiber, the series is due to Bungok in an article in topology, and then Sudi Tang, my student Sudi Tang, and I extended this to the case of several points per fiber. And then there are many papers on extensions of the theory by many people, and here you have some of these papers. And about moduli spaces, you have also a number of papers. In particular, there are two papers by Alessio Figali and myself. And then there is a paper of Joey Palmer about moduli spaces of semi-toric systems. So we understand now the classical semi-toric systems, but does this tell us something about the Weil-Bogner-Moser theorem? And the answer is yes. So what is a quantum semi-toric system? A quantum integrable system is semi-toric if the principal symbols form a semi-toric system. And LeFloc, Bungok, and myself, in some papers, we proved that the spectrum of a quantum semi-toric system determines all classical invariants, but perhaps the K. That is, determines the polygon, the points P1, Pn inside, and the Taylor series. And then in 2021, LeFloc and Bungok proved also that the K is determined. So together with the theorem, the challenge is solved for a toric system. But of course, there is a lot to do because this is dimension 4. So the idea is to prove these theorems is first to detect classical invariance in the quantum spectrum. This is analysis and spectral theory. But since you know symplectic geometry, we know what to look for. And once we have the invariance by the previous theorems, which tells us that the systems are determined by the invariance, we are done. So hence we have constructed bridges between symplectic geometry on the one hand and combinatorics analysis and topology on the other hand, in order to classify classical systems and solve the quantum problem of Weil, Bogner, and Moser in the toric semi-toric case. But there is still a lot left to do, as you can see. So since I mentioned challenges, I want to indeed say that it is a challenge to obtain symplectic classifications of integrable systems in dimension 6 or higher beyond the toric case, which is an arbitrary dimension. This goes back to the question that you asked me earlier. Even in the semi-toric case, there is too much freedom in the singularities as singular fibers. So in particular, if we don't understand classical systems, it's hard to solve inverse problems for quantum systems because you don't know what invariance to compute. So progress on the symplectic geometry of integrable systems in the past 2 decades has been remarkable. Despite of this, current methods do not seem to be powerful enough to break the dimension barrier more than 2 degrees of freedom, meaning higher dimensional manifolds, or deal with general systems. So the field, in my opinion, can benefit from incorporating techniques from other areas. And the recent work on Ewald's conjecture, which uses polytope theory, is an example. And in a recent special volume, in honor of my geometry teacher in a paper, I listed some open problems, and I'm going to conclude by mentioning 3 of them. So I'd like to thank Leonid Polterovich for explaining to me some of these questions, and I hope I understood them correctly. So by Floer theory, one can get a non-trivial measure. This is work of Entov and Polterovich on the image of an integrable system on a 2n manifold to Rn, which helps detect these non-displaceable fibers. You see, this question of displaceable, non-displaceable fibers is very connected to Ewald's conjecture. And there is work on this by Polterovich, Rosen, and Polterovich. And then Dixten, Ganor, Polterovich, and Sapolsky developed recently a categorification of quasi-stakes. The image of F contains a structure called an ideal value measure. So a problem that I propose is, can these or similar techniques be used to construct invariants of integrable systems? For example, foliation invariance replacing the polytope. And I remember that more than 10 years ago, I gave a talk in the Institute in Princeton, and already Helmut asked me this question. So you can see it is still a problem that we don't know how to do. But it would be nice to find analogs of these polygons in higher dimensions, and they have to be replaced by something more general, and foliation invariants, what type, etc. Another problem is to use J-holomorphic techniques to give other proofs of known results about integrable systems or prove new ones. And finally, can displaceable or non-displaceable fibers be detected in the spectrum of a quantum system? So I conclude with a last challenge. IAS Professor Vladimir Voivodský passed away in 2017. Of course, a very famous mathematician, Fields medalist, and one of the most important figures in algebraic geometry and topology. In 2015, Voivodský, Michael Warren, and I published a paper taking the first steps in p-adic integrable systems. And the question is, can one carry out the symplectic quantum geometry I just discussed if you replace the field of real numbers by the p-adics? So this is a great challenge, in my opinion. And the paper I just mentioned with Warren and Voivodský sketches some basic ideas about the p-adic systems, gives the basic definitions. And Luis Crespo and I had been working on a p-adic James-Cummings model, and there should be a paper very soon ready. But very short computations in the real case have turned into very long computations in the p-adic case. So I think the theory of p-adic systems is going to be extremely interesting. And of course, the literature on integrable systems is very extensive. The work I have presented today has been influenced by my teachers, students, mentors, collaborators, and many authors. And here you have some papers, some influences for this talk, and some very famous work by a number of authors. In particular, I have been very influenced by the Hofer-Sender book on Hamiltonian dynamics. And I conclude with the words of Moser, who, if you heard talks that I've given in the past, you know that I really like to cite Moser because he's one of my heroes. So in a times of dangerous specialization, we should feel free to use all tools available to us and use them with proper taste. To me, it seems idle to argue whether to prefer solving of challenging problems, building of abstract structures, or working on applications. Rather, we should keep an open mind when we approach new problems and not forget the unity of mathematics. So this concludes the third part, and these are some articles which concern this part. Thank you for your attention.
Thank you. Thank you very much. I'm not sure, I mean, given what you told me, I'm not sure if you have time for questions or
so maybe I myself went over time, so but maybe maybe there is time for briefly. I have to run to a meeting, but maybe one question or so.
Yeah, I don't know if there is one question.
So can you say something about this Taylor series? So what exactly it calculates?
Yes, so this Taylor series does exactly the following. It classifies a neighborhood of of a fiber which contains any number of focus points up to symplectomorphisms. So imagine you have your fiber, say, with 5 focus points. Okay, then for each of these points, you have a Taylor series. And then these 5 Taylor series classify a neighborhood of this singular fiber up to symplectomorphisms. So up to symplectomorphisms which preserve the system. So it's a semi-global result which gives a symplectic classification of a neighborhood of a focus fiber, of a fiber which contains focus points. And these Taylor series come from, you can have any finite number of them. They come from analyzing the behavior of the Hamiltonian vector field generated by F1 and by F2. One of these vector fields is periodic and the other has some sort of hyperbolic behavior. and which is very singular as you approach the singularities. And there is a procedure to desingularize this behavior, and you get this Taylor series. So short answer, this collection of Taylor series give you a classification, very important, symplectic classification of a neighborhood of the fiber. So this is essential because you understand completely the system in a neighborhood of a fiber. So our techniques are mostly cut and paste techniques. So this allows us to look at the real part given by action angle coordinates of the system and glue these neighborhoods of fibers, these neighborhoods of focus fibers, which are determined by these finitely many Taylor series. And then that gluing is delicate, but yeah. Does this answer your question or?
Yes, thank you very much.
Sure.
Okay, so then I suggest that we thank Álvaro again. Thank you very much.